Hello everyone. We'll discuss the differential equilibrium relationships in today's class. So this comes after our discussions in the last class about the distributed loading and the resultant of the distributed loading and so on. Okay, so this is another alternate way. This differential equilibrium relations is an alternate way to obtain the internal forces and moments along a slender member, and we have seen a few of them now. So this is sort of a new method to solve this. And what we do in this, that instead of cutting a beam in two and applying the equilibrium conditions to one of the segments, we consider a very small element of the beam as a free body. Then we apply the conditions of equilibrium on this small element, and doing so gives us a differential equation which connects the load, the shear force, bending moment, and so on. And once you integrate these relationships, you get a internal force, shear force distribution and bending force distribution. So let's see how that works. Have a look at figure 3.14. This shows a beam of length x. Okay, so the length of the beam, sorry, there's a small part which is of length delta x, and then there's an external actions on this element are distributed load by intensity q acting over this length delta x. Okay, the shear forces and bending moments on the two faces are shown in this 3.14 B. So what you have done is you have just taken this particular thing out and zoomed it, and O is the center of this small part of this beam, which is of length delta x. Okay, you have applied the intensity over here in this length delta x. It is supposed to have some variation, so q of x is what you put over here. Now look at this part. Start on the left face of this element. The shear force acting is V, and the bending moment acting is MB. When you come to the other side, other face of this small element, the shear force is supposed to be V plus delta V. The signs are there to keep it in equilibrium, and similarly the bending moment also has this delta MB. Okay, so this is the change which has happened in the shear force and in the bending moment coming from the left to the right. Okay, for this small element. So just rub this parts. Okay, now look at C. Okay, 314C. What you have done over here is you have replaced this equivalent, this distributed load, by an equivalent force. Okay, by this resultant force R, and you should in theory you should actually compute R and its location according to equation 3.2. What was 3.2? If you check back, that was this. And x bar, meaning where does this act, is actually 0 to L x q dx by R. This was 3.2. So this is what you should have actually done to write this. But if the variation of qx is smooth and delta x is very small, then R is very nearly given by qx. Okay, q into delta x, and the line of R will very nearly pass through the midpoint of the element. So it all depends on the smallness of this delta x. This is so small that taking this in the center and taking this as essentially taking basically a behavior like this, essentially something like this, is not a big deal. Okay, So this is what we mean. So that's why you have a q into delta x multiplied, just because of the smallness of this element, which is delta x. And this idea comes in at many places. Okay, so it's not new or new or unique to this treatment which we are doing over here. Okay, so since you have sort of figured out that you can replace this r as q delta x, and it must be in the center of this small element. So now you would want to write the equilibrium equation that delta x is satisfying. So let's see what those are for this C. So you will have a summation. So this for C is what you want to write the equilibrium equation. So one is V plus delta V plus Q delta X. Okay, this is all acting upwards. Then there is a V acting downward over here. So that is equal to 0. And similarly, now you would balance the moment about O. Okay, so one is clearly the right hand side, which is MB plus delta MB. That's one. Okay, then the other right hand sides would be V plus delta V, and the lever arm for this is delta x by 2. So half of this distance over delta x by 2. Then acting in the negative direction would be your MB. Okay, and you have another V into delta x by 2, the moment due to this force, moment due to this force about O. That is this term, and the sense of it is the same as for this one. So if you take a R cross F, you get the same sense. That's why you have a positive sign, okay, coming out of your screen right now. Okay, so this is the force and the moment balance, and you want, before you actually take this limiting process of delta x tending to 0, you must do this. So this is 3.9, and you are basically rearranging 3.9 to write it in this form. Okay, so basically this and this gets cancelled, and you divide both the sides by delta x, because delta x is not equal to 0, and you would get this. Similarly, this gets cancelled with this, and v delta x can be taken twice. So let's see, you should get delta mb by delta x plus v equal to minus delta v by 2. Let's just check this last statement if it's actually, so this is equal to 0 definitely. So this gets cancelled, so delta mb is there. Okay, nice. And v delta x by 2 is actually there twice, so that gets added. Okay, and then you have a delta v into delta x by 2. Okay, so that's over here. So this is what you get when you rearrange this equation 3.9, and now you can use this limit that delta x tends to 0, and that would give you dv by dx plus q of x is equal to 0, and dmb by dx plus v of x is equal to 0. Now there are some things to note over here. First of all, I'm not using a partial derivative because v and mb are only dependent on the position. Okay, so that's why a normal derivative is okay. And then you will also see a minor difference, say in this equation. Okay, and that occurs over here as 0. Can you think of a reason why this is like this? I mean, why when you apply this limit delta x tends to 0 on this one, you get this particular term. I mean, it's obvious in the sense when delta x tends to 0, okay, delta v will also tend to 0, and that limit has been applied on this side. Okay, so that's what we mean by this, and the reason for all this is because of this continuous distribution which we have. So it's quite straightforward over here. And that is, I mean, even physically you can try to argue. Look at this diagram over here. Look at this B diagram over here. So if you make this delta x really small, there would hardly be a, if you make this delta x is really small, there would hardly be a delta v or hardly be a delta mb. So when this will tend to 0, this will also tend to 0, and this will also tend to 0. So that's the argument which you can make it. Okay, in the limiting case. Okay, now once you are done with this, you have this 3.11 and 3.12. Okay, extremely important differential equilibrium relations. And you have the load intensity Qx, shear force Vx, bending moment Mb. Now equations 3.11 and 3.12 can be integrated from a section x1 to x2, and then you have the internal force distribution. In the sense, you integrate this from x equal to x1 to x equal to x2, and you would get the all the values which you would need. Okay, so once you integrate this, you should be able to get v of x2 minus v of x1 plus x1 to x2 q dx is equal to 0, and similarly mb of x2 minus mb of x1 plus x1 to x2 v dx is equal to 0. So let's consider an example of where we can apply this knowledge. So this is example 3.5, and you want to use this differential equilibrium relations to solve this problem. So you have a Q, I mean the intensity is given to you, that is W naught, and given the X and the Y direction which you have chosen, you would want to write this is the actual situation. Okay, this is a model. So the roller is, you are assuming that it allows a free movement in the horizontal direction, and hence it will not offer any substantial frictional force. So that's why you only have a RB. So this is a model which shows essentially all the forces, and you have a pin joint at A. By the same logic, I mean the pin, because you don't have a frictional force over here in the x direction, similarly there is no point in considering a horizontal force over here, because even if you did individually consider, because there is nothing on this side, it would be 0 for equilibrium. So you don't want that. Okay, so the free body diagrams are shown in this 3.15b, and the reaction B is directly vertically upwards. Since the loading is also vertical, the remaining reactions RA at the pin can only have a vertical if the beam is to be in equilibrium. So we already discussed this. Now look at 3.15c. We have sketched the loading diagram. Q is equal to minus W naught. So what this diagram tells us, that for the whole length of the beam from 0 to capital L, and it shows over here, the intensity is minus W naught. Okay, so if Q is something which you take positive, because it's acting over here in a downward direction, you'll have to take it a minus W naught, and it's constant throughout. So that is what this line shows. Okay, now let's write 3.11. 3.11 is over here for this particular case. So that would be dV by dx minus W naught, because Q of x is minus W naught and it's a constant. So that's what we are writing. Okay, and now you can perform a indefinite integration. That would mean you have a V is equal to W naught x plus C1. Okay. Okay. So this is how you have integrated an indefinite integration. So you essentially get a shear force, of course, provided you must find this constant C1. So now the challenge is to how to find this C1. I mean, we can't leave the problem over there. So you look at x equal to 0, okay, at this end. The shear force over here is actually equal to minus RA. Okay, so sorry, RA, and at x equal to L it would be RB. But the only problem is you haven't actually calculated RA and RB until now, so there's no point in using it. So you want to use it as an initial or a final condition, but there's not much you can do. But so let's keep C1 for now. I mean, if we had known what RA and RB was, we could have found out C1, but right now we don't. So let's keep it like that and then proceed to 3.12, this equation, and integrate it. So let's write it dmb by dx. What is v of x over here? We have just found out. Okay, so we'll write plus vx as plus omega naught x plus c1 is equal to 0. And now you would want to again perform an indefinite integration, and this time I think you'll have these quadratic terms. That would be mb of x will be plus half of w naught x square plus c1x equal to c2, where c2 is also a indefinite integration, constant of indefinite integration. So you have actually solved the problem. The only thing is you must find c1 and c2. So is there an easy way? Yes. I mean, one thing for sure is, irrespective of whether we have a shear force at the ends or not, there is definitely no bending moment at the ends, which is x equal to 0 and x equal to L. So we can write that MB is equal to 0 at x is equal to 0 and MB is equal to 0 at x equal to L. Using these two conditions, we can find the value of C1 and C2. Okay, use these two conditions in this equation and you will be able to get C1 and C2. And once you have C1 and C2, essentially you have your shear force and bending moment diagram. Okay, so you will find out that this is true, and once you have these two things, you can draw the shear force and bending moment diagram. Okay, one of the important things which you should note right away, that unlike the previous cases, you did not actually ever find what RA and RB was. Okay, so that's where this is a unique method. And but now since you have these solutions, it is easy for you to find what RA will be. So what you have to do is x equal to 0 V will be equal to RA. Similarly, X equal to L, V will be equal to RB. So you can have RA and RB, but it was not actually needed to find the distributions of force. Okay, so this is something which you can keep in mind. All right, so this uniformly loaded beam is actually very important, and many of the constructions and bridges and things like that, they have a uniform loading, and you have seen that the center of the beam seems to be having the maximum bending moment. Okay, is and one of the other important parts about this is that the bending moment is maximum when the shear force is minimum, which is 0, and the bending moment is minimum when the shear force is maximum. Okay, so this is something which you should be noting over here. Okay, so let's move to this next part. I mean, not very different. So you have this beam which is of total length L. The difference from the last problem is now this uniform loading is only until a certain point, which is x equal to a. And from x equal to a to this final length L, there is no force at all. Okay, not either distributed or concentrated. There is no force at all. So this is the problem which we want to consider. So let's see how we can deal with it, and we'll have to deal with it in two separate ways, obviously. I mean, you already know this. So let's start with dividing it into two parts. Okay, and first of all, take this first part. I'm in left of this part 1. This will be part 2. Okay, and we'll again use 3.11 and 3.12. Where did it go? Over here. Okay, so 3.11 and 3.12 are extremely important, and we'll be using them in our case. So let's apply it on the first segment. So I will be using a subscript of 1 to show which part I am in. So dv1 by dx, meaning the shear force in this one part, minus w naught is equal to 0. And in the second part, this part, you want to write 3.11, that would be dv2 by dx, and there is no loading, so this will be equal to 0. So you can have this integrated indefinitely, v1 minus w naught x equal to c1, and v2 will be equal to c2. Now you want to write 3.12 in these two parts. For the first part, again you will be writing dmb. So this is just the previous case in which you had a uniform loading, x plus c1 is equal to 0. Okay, so this c1 is coming because I have just substituted v of x. This thing I have just written from over here. Okay, v1 of x, and then you have the other part which will be dmb2. Sorry, this is dmb1, this is dx plus c2 is equal to 0, and you will now get mb1 and mb2. Okay, and you will have these lots of constants now, and in mb1, if you this, so if you integrate this, you will add one more constant. Integrate this, you will have one more constant. So let me just write it out for the So C3 is the constant of indefinite integration. Once you integrate this one, and this becomes plus C2x is equal to C4. So the boundary conditions at each end is again the same as before. I mean, let me write the boundary conditions. So at x equal to 0, mb1 is equal to 0. At x equal to L, mb2 is equal to 0. So that will at least solve two of these four unknowns, C1, C2, C3, C4. So two unknowns you have found out, but you will still need information. I mean, there are still two more unknowns left. Okay. For this, you have to follow the equilibrium requirements at the junction. So equilibrium at junction for the remainder two constants. So junction is x equal to a. At that point, because x equal to a is still an internal point of the beam, so v1 must be equal to v2 at x equal to a. Okay, and similarly mb1 will be equal to mb2 at x equal to a. Okay, so once you insert all of it, you should be able to find the other two remaining constants, and you will be able to find v1, v2, m1 and m2. Okay, so you should be able to easily plot these values, and you see why where this thing is coming. It is showing up in our graph over here. Okay, not differentiable clearly, but definitely continuous. This shows up over here, seems continuous and differentiable. Okay, so that's how you solve using the differential equilibrium conditions, and you have seen how easily things can be solved. So we have to be aware of all the tools which are there to solve problems, because different problems require different tools. So our job is to be comfortable with all the available tools which are out there. Okay, so another and perhaps the last topic to learn over here is the singularity functions, and we will see that they are extremely useful when the loading is of a complicated nature. Okay, so let's see what do we mean by them and how we can actually use them in the concepts, in the problems of this course. So in the foregoing section, we demonstrated how the relatively routine procedure of integration could be used for shear force and the bending moment diagrams. We have seen that. There are situations where there is a concentrated force, okay, or there is a sudden change in the loading. I mean, there is a loading and suddenly there is a change. Either it becomes zero or it becomes very large. And this problem becomes very hard then. You have seen this in this problem where there was a sudden change in the loading over here, and you see how complicated the integration became. Okay, and imagine there are a few more situations like this, then it will be a very lengthy integration to do. So that is the motivation why we want to have some other method to solve to solve problems like this. So we have this family of singularity functions defined, and the figure in front of you, 3.17, shows 5 such functions. And let me just define what they are. So first thing is to write this fn of x is equal to x minus a to the power of n. You have to note two things, that this brackets are of this type. You cannot use any other kind of a bracket over here because this denotes what a singularity function is. Now, when n is greater than equal to 0, so this is 315, equation 315. When n is greater than equal to 0, 315 has the following significance. If expression in the pointed brackets is negative, meaning x is smaller than a, the value of this function is 0. If the expression in the pointed brackets is positive, then x, meaning x is greater than 0, then the value is fn. So if, let's see, if x is smaller than a, then fn of x is equal to 0. If x is greater than a, then this function becomes equal to x minus a to the power of n. Okay, and this is when n is greater than equal to 0. So thus the pointed brackets are like ordinary brackets except for one idiosyncrasy, that they are blind to negative values. Now the function x minus a to the power of 0 is called a unit step starting at x equal to a, and the function x minus a to the power of 1 is called a unit ramp. So this is called a unit step, this is called a unit ramp, okay, when n is equal to 1. And then you can have the integration laws just like in the same way. So you see, for this function will always have a value which is equal to 0 for a value of x minus a being negative, so x smaller than a. Okay, so we want to integrate this function. And why do you want to integrate this function? Because you have seen in the previous section there is an integration step required. So you do expect integration over here, and we'll see in problems how does that work. Okay, so you want to do this integration, and it seems life is very easy, because from minus infinity to 0 for that matter, or I mean x minus a equal to x equal to a, I mean there's nothing much happening, so that you can just write it in this form, all for n greater than equal to 0. Now the first two members which you have is clearly of a case when n is smaller than 0. So just to make this slightly more differentiating, notice that the subscript is written over here, and in other cases you have the superscript. So this is the superscript, okay, and for -2 and -1 you have the subscript. So that's one way just to distinguish it. It's a special case. And these functions, what about these functions? These functions are 0 everywhere except at x equal to a, where they are infinite. So this function and this function is 0 everywhere except at x equal to a, where it is infinite. Okay, so but they are infinite in a way. So these are properties which are defined to this. Okay, so this is a definition, if you would want to say, x minus a. Again we have to put this integration, because I mean integration will be required at some stage. So dx equal to x minus a minus 1. Similarly, you will have a minus infinity to x minus a minus 1 dx x minus a 0. Sorry, it should be a Well, 0, I don't know whether you should write a subscript or a superscript, so let's just write a superscript because we have already done that over there. Okay, so x minus 1 is called a unit concentrated load. Sorry, this one is unit concentrated load, and x minus a minus 2, it is called a concentrated moment. So in physics they call this as the Dirac delta function, and this is called the impulse function. So just, I mean, if you would want to see this someplace else, I think you will have this there. So the integration laws, which I have written down over here, I mean this one 3.17 and this one 3.16. Okay, they allow you to do these integrations, which eventually help you find the bending moment and the shear force diagrams. Okay, so let's look at. I mean, there is also an equivalent. Moments diagram. So this figure 3.18, if you look, illustrates some example of load intensity distributions and how they are represented by singularity functions. Okay, so if you have a concentrated force, okay, this one, you have a minus 1. If you have a concentrated moment, you have this one. You have a horizontal uniform loading, you will write your intensity in this form, and then you have a ramp or linearly increasing, like the hydrostatic pressure sort of an intensity, you write it in this form, just like using this over here. So nothing new. So first thing, I mean, it's not that there are only these 5 functions, there are a lot, but for our sake and our problem, these 5 singularity functions are enough to solve it. So most practical cases of beam bending can be built by superposition of these cases, these 4 cases which you are shown. This will also be seldomly used, this one. Okay. So as I've said, they can be used to solve problems. So let's solve a problem and convince ourselves that it actually works. So look at example 3.7. In this example, you have what we want to do is consider this problem again. I mean, remember this problem in which there was C1, C2, C3, C4, and then you went about finding, applying the boundary conditions of the moment at A and B, and then you applied the conditions at the junction. The shear force and the bending moment have to be the same. So this problem we now want to solve using this singularity function. One thing which you would notice is that the problems keep on repeating themselves. Okay, it's just the method which keeps on changing. The reason is so that we can compare how good or bad or lengthy the method is compared to the others. Okay, and the good part is that eventually you have an answer to match. I mean, if the answers are not matching, then there's a problem. I mean, you should get the same distribution as you would in any other case. Okay, so you have the same problem and you want to now solve this using the singularity function. So if you look at 3, so this was the actual problem, this is the model, and one of the things which you should notice over here, the intensity, if you look at these 4 options in front of you, there is no option for qx equal to 0. Okay, this does not exist as a singularity function, and you would need that in this part, right? There is no intensity in this part, so ideally you are staring at something like this. To get around this, what they do is this: they apply the same force in opposite directions on this part. So in effect, it's as if there is no force over there, and they can still do apply the singularity functions over here. So that's why this model is slightly different from the previous case. Okay. So this, because this will allow us to use singularity functions. Okay. So the way to read is this: the load intensity can be written as Qx is equal to minus W naught plus W naught x minus A. So what they do is, with this minus W naught, they write this entire term, okay, from here to the entire end, and then they add this other term which is a positive W naught, but it only begins at a certain point which is at x equal to. So you are using this part, this figure over here. Okay, so there's a 0 over here. So at x equal to a, suddenly you have this uniform loading beginning, this particular part, and that you can write as this. So that's what you have over here. Okay, so this is how what Qx can be written for all x element of 0 to L. Okay, now what you do is you substitute this into 3.11, and then you would find that v of x is equal to W naught x minus W naught x minus a 1 plus c1. How would you do? I mean, you have integrated this, okay, and the integration laws, you have seen how that works. So this is the integration law, okay, and similarly you want to have v of 0 is equal to c1. So but that is actually equal to minus of Ra. So that way you can find the values, and similarly you have to find 3.12, and MB is what you would have. Okay, so you can just make those substitutions, and then you will also get a C2 somewhere in this one. This you have to find out by putting in MB of 0 is equal to 0, and you should get a C2. So using this, you should be able to draw the shear force and bending moment diagrams. Okay, so you have these diagrams C, D, E, and F, because they are actually solved separately, and you have a final sort of mix for all of them. Okay, so there is this thing, but when you superimpose this with this, you get this. Okay, so this just gets pulled down by a certain value. Same applies for the bending moment as well. So this is how you would solve this problem, and you can have a look, and you will eventually get the reaction forces as well. So in this one also you do these integrations and solve. The advantage is because the integration of the singularity function is known beforehand, many of these calculations are easier and faster to do. So this is one other method which you should use, and you should definitely know this for your course. Okay, so this is where I mean, there are a couple of things, a couple of examples which we always sprinkle around and leave from the course, but it's not that they are not included in your syllabus. We just don't feel that everything in the textbook has to be discussed in lectures, because you actually are reading the textbook by now, and if you are not, you are making a very big mistake. You should be reading the textbook word by word, line by line, from the first word itself. Please don't skip anything, otherwise it will be a big problem. Okay, so We have only been using two-dimensional problems until now, but it should not let us believe that it's only two-dimensional problems which are important. Okay, so that's why we'll just briefly go through this three-dimensional problem. The objective is the same, okay, to find the shear force and the bending moment diagram. And to make it slightly more complicated, we are taking it in the radial coordinate system, not the Cartesian one. Okay, so I'll just go through this once easily, and you can see if all of it is okay. Okay, this is just to like let that fear go away of a three-dimensional problem. Okay, because the concepts are exactly the same. So there should be no fear of a three-dimensional problem if you are ever asked to draw the shear force or the bending moment diagram, because in reality all the problems will be a three-dimensional. Okay, so take a curved slender member. Okay, you have a slender member which is clearly curved now. You see that over here in figure A, and you have it's a piece of refinery piping, perhaps hydrocarbons, petroleum products pass through this pipe, and it is anchored at B and bent into a quadrant. So this is the anchor B bent into a quadrant at A. The center is O, radius is A, so it seems all easy. You want to obtain the force and bending moment diagrams for this segment of pipe when a transverse load P is acting as shown. So this is the external load acting. In the presence of this load, what is the shear force and bending moment diagram for this problem? Oh, that's what it is asked. So there are some basic things which you need to do. Since it's a radial coordinate system, you will have to do it slightly more carefully, perhaps because most of the problems which we did until now were in the Cartesian system. But it's easy. Let's see. What you do is you make, just like in the earlier cases you had a x and then you had a small part delta x. Here you have this theta, so you want to have this 0 to a and then theta. Okay, you already have this over here, so let's put out all these terms. So a is the radius, theta is the angle. You are at this point C, and this C is the point which is of interest to us. Okay, so you define this new coordinate system which is XRS. Okay, so you have S, I mean, because part of the problem is in the radial, part of the problem has to be in Cartesian, so we'll see how that works out. So let's see. One is that you have a x, y and z coordinate system. Okay, the origin is over there, no doubt about that. You now want to introduce a new coordinate system at a point of interest. This is the point of interest. Okay, so you have a x, but now you have a r and s. So this is where the radial part is coming in, and this r and s is chosen such that this r is tangential to the curve, sorry, normal to the curve, and s is tangential to the curve. So this is a system which is chosen at the point of interest, and it is where you would want to make this hypothetical cut at C. Okay, so one of the things which you can easily write is that you want to now come or measure this distance in terms of S. So S can be written as a theta. Okay, so this is something which you knew, part of the circumference r theta coming from there. R is the radial distance from the O. Okay, so the force P at the free end A can be held in equilibrium by force Vx. So you have a shear force Vx. And why do we need it? Because we know there's a P staring out here. And since there is no other external force, so this is the only shear force which we'll have. There's no point in taking, say, a VR or VS, okay, because there is no other force, external force. So the only force is in the direction of P, and that will be ensured by taking a Vx. Okay, so that's the first thing. And then you will have torques MSS and SR. Remember what MSS was? It was on the sth plane in the sth direction. MSR will be on the S equal to something plane in the R direction. So in the R direction, in the S direction. Okay. So once you have this, you have to just do a force balance. That would be P into I cap plus Vx into I cap equal to 0. Then you have to balance the moments about C. So MSS into, look at this unit vector US cap. Okay, it is in the S direction, this direction, plus MSRUR cap plus RCA cross PI cap. This is equal to 0. Okay, now you can easily find what RCA is based on the geometry. You can also write J is equal to, J cap is equal to UR cos theta. This is something which you may have done last year in your mechanics course when you wanted to transform coordinate systems. Okay, so there was a rotation matrix, and you may have done it for actually I, but you can do it for any matter, for anything for that matter. And small things like this you can also do it by geometry. So you can utilize this particular C diagram to arrive at this, because this is easy, but better you should know the transformation. And transformation you must have learned in your course in linear algebra. I don't know what maths course that is, but wherever you have this linear algebra, you should be able to do that. Okay, so once you have this, you will get the value of Vx, you will have a value of MSR and MSS. So just like a discussion on this particular topic. So with this we end this revision, meaning we have discussed all the theory, and there are parts which you have to read yourself from the book. Everything which is not discussed has to be read, everything which is discussed have to be read from the book. And now on we'll begin with chapter 4, which is the stress and strain, and that will remain with you for a very long time in your life. I don't mean the stress, but the stress of solid mechanics, stress of continuum mechanics. So we'll discuss that in the next class. Thank you.